Hello, good morning or good
There we go.
afternoon. Thank you everyone for joining us today in our webinar series. In this session, we're going to be discussing the basics of dust collection system design. So my name is John Daniel. I head up our engineering efforts here at Donaldson Company. We also have Amy Miller on with us today, who's our training manager. She's working behind the scenes and will be moderating the Q&A at the end of the session.
Thanks to all of you for joining us today. Please make sure and submit questions into the chat box as you think of them, and Jack and John will address them at the end of the session.
Yep, thank you, Amy. Obviously, we're going to start off discussing the basics of dust collection systems, why it's important, what we're collecting, and some common applications. And then we'll talk about each of the primary components for a dust collection system, including the hoods, the ducts, the collectors themselves, the fans, and the controls. And then we'll wrap up with a Q&A session at the end. Just a heads up, and as you'll learn today, dust collection is a very complex issue, and the system design is very complicated. It can take years of experience to develop expertise in it. And today's goal is just to give you the basics of dust collection system design. In case any of you aren't familiar with Donaldson Company, we've been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first tractor engine filter. Today, we're one of the largest providers of unique filtration technologies. We excel at producing high-quality filters and equipment. We pride ourselves on having a global reach with a local touch. Our world headquarters is here in Bloomington, Minnesota. We have about 56 manufacturing plants and 21 distribution centers around the world. During the session today, if you're wondering how to engage with us, there's a couple things. Obviously, if you have questions throughout the seminar today, please enter them into the chat. You can see the chat on the side there, and we will make sure we get to them at the end of the session. And please think of them, put the questions in as you think of them. And then during the webinar, Jack may ask you a few questions. You can respond with a thumbs up or a thumbs down. You can access by clicking the face icon at the bottom of your screen. And with that, please introduce our featured speaker today, Jack Holtz. Jack's been with Donaldson for over 30 years. During that entire time, he's been involved in engineering, sales, and support of industrial air filtration. He lives in Delafield, Wisconsin. He's a territory manager for our southern Wisconsin market. Prior to Donaldson, he spent 6 years selling marine propulsion systems for commercial and naval vessels, and he holds a bachelor's degree from the University of Wisconsin-Madison. So with that, take it away, Jack.
Thank you, John. Greetings. I would like to start out by asking about your experience with designing dust collection systems. Please use the chat box and type in the letter that best aligns with your level of experience.
Okay, experienced. All right, looks like we've got a fair amount of experience here, ranging from C to E. So you've got a pretty good group here that looks like they're just learning a few more tricks and information about dust collection system design basics.
Sounds like I'm going to have a few questions at the end.
Yeah.
Well, thank you, everyone. It's helpful for us to know the experience level of this group. Let's start with the basics. There's a lot of important reasons to control dust, fume, and mist, including safety concerns, hazards, improving air quality for employees, exposure control, reduce potential dust in breathing zones of workers operating the process, environmental concerns, EPA standards for outdoor exhaust, environmental air quality, outlet emission requirements, and cleanliness, concern about the overall cleanliness of a facility. Many types of industrial processes generate dust, fume, and mist, and within those processes, there are specific considerations to address. Here's a diagram of a typical dust collection system. A blower or fan creates an airflow which is used to capture dirty air with a hood and then convey the material through a series of ducts to a dust collector. Here the contaminant is separated out and the clean air passes through the filter media to the fan where it is discharged to the atmosphere. If one component is poorly designed, the whole system is affected. Here's a real example of a dust collection system. Well, actually, there's two of them next to each other. This is for a welding application that was recently installed. The welding curtains haven't been put in yet. You can see the fan at the top with the silencer for noise reduction. The dust collector, these are cartridge collectors. The ductwork with a spark cooler in it for spark mitigation, extraction arms with bell-mounted mouth hoods at the end of them, and electrical controls mounted to the wall. When we design a system, there's a lot of factors that are considered, probably more than most people realize. The publication shown here is the Industrial Ventilation Guide, written by the ACGIH, which is a nonprofit scientific organization that advances occupational and environmental health. The outlines in it are considered by most in the industry, including OSHA, as the standard for proper ventilation design. The ACGIH offer multiple courses throughout the year on system design, using the Vent Guide as a textbook. I've attended multiple courses myself over the years. If you want to get more into system design, I recommend you check it out. When we think about collecting dust, fume, or mist contaminant, there are some important characteristics to consider, which will help us to determine the type of collector and filter media. In terms of size, some contaminant is visible to the naked eye, while others are only visible using a scanning electron microscope. On the large side of the scale are contaminants such as cement dust, fertilizer, coal dust, and milled flour. On the submicron side, there are contaminants such as weld fume and carbon black. The size of the dust is important because it dictates how the dust cake will form on the outside of the surface of the filter medium. The shape of the contaminant could be spherical or round, fibrous, long and skinny, flaking, flat, or a mixture of different shapes, depending on what type of application it is generated. The photo shows fibrous particles from a fiberglass sanding and grinding operation. In this situation, you'll probably need to specify a particular type of filter media and potentially a specialized filter unit to keep the dust from bridging between the filters. Bulk density is the amount of weight that is measured in a defined volume. It is expressed in mass per unit volume, typically pounds per cubic foot. An example of lighter dust is oats at 26 pounds per cubic foot. And on the heavier side is lead carbonate, which is about 250 pounds per cubic foot. Abrasive dust, such as sand, rock, or abrasive blast shot, will degrade filter media and collectors and closures, so it's important design consideration. Agglomerativeness is a characteristic that will tend to gather the dust into a ball, mass, or cluster. Examples of conglomerative dust are paper, cellulose, and cotton. Special cartridge design and potential specialty bag houses may be needed if the dust is conglomerative. Hygroscopicity, that's a mouthful by the way, is the dust characteristic that will readily take up and retain moisture. Hygroscopic dust examples include acid, starch, and cement. Selecting the right collector and filters is important for dust that retain moisture. There's potential for plugging up filter media. The chemical composition of the dust is also important to consider. It is always a good practice to get the safety data sheets on the dust or material from the customer. This will provide information regarding corrosiveness, toxicity, and explosiveness. These factors may affect the collector and filter media type, material construction, recommended accessories such as bag in and out options, and possibly explosion suppression devices. And speaking of explosiveness, it's important to know that some dust and fumes may present a combustion risk. If the dust or fume is combustible and it mixes with air, like the airflow coming into a dust collector, and an ignition source, the end result could be a fire. And if you add the dispersion of the dust, which occurs frequently in a pulse cleaning collector, you could get a flash fire. Now, if you add in the confinement of the dust, such as in a dust collector housing, you could get an explosion. I wish we could spend more time on this, because it's really a complex issue. For now, it's important to know that if dust or fume is combustible, it's an important design consideration. Typically, we need to know things like who is the process owner, who is the authority having jurisdiction, or AHJ, and if there is any information from their DHA. I wanted to review just a few basic terms and formulas that we will use frequently in system design. The most basic and widely applied is airflow. The formula is Q equals V times A. The Q is the volume of air flowing through the system, often referred to as CFM, or cubic feet per minute. To get the airflow, we multiply the velocity of the air, which is a measure of linear speed through an object, by the area of the hood or duct that the air is flowing through. This formula is one of the basic building blocks of dust collection design. We start at the pickup points and calculate using a formula to get the needed airflow of each pickup. This will then give us the total CFM needed for the system. The formula is also used when calculating the needed velocity within the ductwork. Throughout the design of the system, we refer to Q equals V times A over and over again. There are different types of velocities that are important to move a contaminant through a dust collection system. Capture velocity is the speed of the air at the hood or area of generation. Face velocity is similar, but is the average velocity of airflow crossing the entry plane of the hood. Duct velocity is the speed of air flowing through the duct. Filtration velocity is the speed of the airstream as it enters or passes through a filter media. This is also referred to as air to media ratio, or for us seasoned folks, we may refer to it as air to cloth ratio. And interstitial velocity is the speed of air in between the filters. Just a few more terms to consider. I already mentioned AMR. It is calculated by the actual CFM divided by the total filter area. It is expressed as a ratio, such as 6:1. So 6 cubic feet of air coming in contact with 1 foot of filter media. And lastly, static pressure, which is the resistance of airflow in a system, from things like the collector, the filters in the collector, which will create more resistance when they're dirty, the hoods, and the ducts. Let's get into the main system components, starting with the hood. Hood design is a critical component overall in the system design, which will allow the collection of contaminant. A well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the contaminant where it is being released. It should be designed with good ergonomic principles in mind. It should be compatible with material flowing through the work area, and it should be designed to minimize maintenance and other activities that may disrupt the process. When it comes to assessing an existing system, a few common mistakes I see are the wrong style of hood being used, the hood is not located in an effective position, or you have inadequate airflow at the hood. A closed capturing hood is generally the most effective method of capturing material. The 4 most common types of capturing hoods, in order of increasing effectiveness, but also increasing fabrication cost, are the following: the raw edge, the flanged, the taper, and the bell mouth hood. Regardless of the style of hood, in order to be effective, a hood must be positioned properly relative to the point where the contaminant is being emitted. To minimize air volume, the hood must be as close as possible to the capture point without disrupting the process. A hood positioned twice the distance from a contaminant emission point, rather than at the capture point, will need to draw approximately 4 times the amount of air to produce the same capture efficiency. And as we all know, the more air means a larger equipment, larger ducts, larger collector, larger fan with higher horsepower, all of which adds up to more capital and operating costs. Sometimes the hood is integrated in the process, like the hood in the picture, which is a taper hood for the enclosed conveyor belt. When determining the required airflow at the hood, the main design factor is capture velocity. To give you a few examples, a thermally generated dust velocity is typically around 100 to 250 feet per minute, depending on the application and the style of hood. Wood dust is typically around 150 to 500 feet per minute, and rock dust, which tends to be much heavier, is typically around 400 to 500 feet per minute. Too much airflow at the hood or pickup point may mean you're picking up good product rather than just nuisance dust. It could also increase your risk of capturing unwanted materials such as sparks or embers. And since more energy is required to move more airflow, it will lead to higher than expected, potentially operational cost. Inefficient airflow at the hood could result in additional housekeeping requirements, and depending on the dust, may lead to an increased risk of employer exposure.
Hey, Jack, sorry to interrupt you. Just wanted to, share the QR code here that's on the screen. And as we mentioned earlier, we do this series of webinars where we focus a little bit more specifically into the different elements, and we do have one coming up specifically on hood design next month. So if you scan that QR code, and I think we have it a few more times in the presentation, it'll take you to our events page where you can register for the upcoming deeper dive into each of the specific components. So thank you, Jack.
Thank you, John. Once again, we designed the proper hood to capture the contaminant. The goal is to move the particulate to a filtration system through a series of ducts. A properly designed duct system should pull the minimum airflow required at the hood, maintain velocities required to transport the material throughout the duct without dropout to the filter element, and if you have to be able to do this by utilizing the least amount of energy as possible and minimizing any wear or tear on the duct components. A few common mistakes that we see when it comes to duct design are the incorrect type of ducting being used, the incorrect duct size or fitting being used, and the duct system not being properly balanced. Minimum duct velocity is a critical factor when it comes to duct design. Typically, we size ductwork to maintain the transport velocities between 2,500 to 5,000 feet per minute in the ductwork. If the dust is combustible, NFPA typically requires a minimum conveying velocity in a duct of 4,000 to 4,500 feet per minute, depending on the material being collected. If the duct velocity is too low, dust could settle out within the ducts and could cause problems, especially if the dust is combustible or flammable. If the duct velocity is too high, it could create safety concerns such as sparks or abrasion, as well as demanding higher energy than needed. Just a few quick pieces of advice when it comes to duct types. Rectangular duct is commonly used in HVAC applications where you're just moving air. But we don't want to use it in industrial applications because it could allow dust to settle out in the corners. Rectangular duct can be used occasionally on the cleaner side as long as the duct vibrations are mitigated. When specifying industrial duct systems, make sure to call out round, heavy-duty gauged industrial ductwork. Most dust collection applications use Class 2, Class 3, and Class 4 ductwork, which are designed by SMECTA standards, which stands for Sheet Metal and Air Conditioning Contractors National Association. Spiral duct tends to leak air, cause undue restrictions, possible dropout of material, so use it with caution. And be aware that flex duct requires significantly more energy than traditional hard ducting, so we recommend minimizing it as much as possible. And lastly, you want to avoid any T's or 90-degree angles in your ductwork because they generate a lot of static. Elbows, pictured on the left, should be of 2 to 2.5 diameter centerline radius, except where space constraints come into play. In some cases, you can use 1.5 diameter centerline, but if the elbows are mitered in 90-degree turns, all that air must slow down, turn, then speed up. This creates a ton of turbulence, which also adds more energy consumption and higher static pressure to the system. The same thing goes with branch entries, pictured on the right. You can see that, looking at that, a 30-degree angle is preferred. I mentioned earlier that having an unbalanced system is something that could go wrong with a duct design. When customers add new equipment to existing systems, they often don't consider the impact it'll have on the other equipment. In most cases, existing systems aren't modified to accommodate the additional airflow and static, and thus becomes unbalanced. Give us a thumbs up if you've ever designed a system only to find out later that the customer changed something that affected it.
Yep. Obviously, we've got a few here that they've run through this scenario before, Jack.
Unfortunately, this happens to me too. If you know a customer is going to be expanding their process, there are ways to design future lines into the system so they don't have to sacrifice performance. Our webinar on duct design is scheduled for October 21st. So again, you can register on our events page if you want to learn more about it. Our next system component is the dust collector itself. The main objective of the dust collector is to deliver sufficient efficiency while operating in a predictable, stable, economic fashion. The most common mistakes or things that could go wrong include the wrong filtration technology, incorrectly sizing a collector either too aggressively or too conservatively, or poor installation. The two most common types of collectors are cartridge and baghouse. But if those don't work for your application, there are others, such as mist collectors for wet machining, fume collectors for applications like weld fume, cyclones, which are often used as pre-separators or for smaller woodworking applications. And finally, there's power core when the size constraints are an issue. Let's talk about cartridge collectors first, since they're the most common type specified and sold today. I always start by considering a cartridge collector and only consider other types if the cartridge collector won't work. Donaldson actually introduced them back in the 1970s, and they have come a long way since. They are smaller in size and have lower initial costs than traditional baghouses. And the filters are much easier and faster to change out. They are best for low to medium-sized dust loads, as well as fine, uniform, and dry dust types. Cartridge collectors utilize typically a pulse jet cleaning system that uses compressed plant air. Cartridge collectors use cartridge filters, and they come in various sizes and shapes depending on the type of collector. There are different media types for different applications. These are just a few of ours. It's important to specify the right one that will work best for an application. For example, if the dust is fibrous and you're specifying a cartridge collector, you're going to want to specify fiber web media or something similar with large pleat spacing, or the customer is going to have issues. And if the dust is conglomerative, you're going to want to specify a cartridge filter that has spun bond based material, or the customer again could have issues. If you know that a cartridge collector is the best solution for a customer's needs, then it's a matter of determining which to specify. It's important to work with an expert who can help you in this process because there are quite a few options, and it's really important to size it correctly. Baghouse collectors. They've been around for 100 years. Our baghouses use anywhere from 6 to more than 900 felt or pleated bags to filter dusty air. They are best for higher dust loads, and they are more forgiving on challenging dust types. They are typically much larger in size and unfortunately more labor intensive when filter changeouts than a cartridge collector. Baghouse collectors are used in different industries, including woodworking, grain, food, cement, sand, and paper. Baghouse collectors use baghouse filters. The two main types are fabric or pleated. Fabric bags are installed over metal cages. During filter changeouts, the entire bag and cage are removed from the collector. The used fabric bag is removed from the cage, and the new one installed around it in its place. Then it goes back into the collector. Pleated bags are a one-piece design. They tend to be shorter in length and take significantly less time to change out. But not all baghouses can use pleated bags. But they are a great option in certain applications, especially if the dust is abrasive. As you can see, there are a lot of options to choose from when it comes to fabric bag medias. So work with an expert who can help you with determining which to specify for the project. For example, a polyester filter might be a great option for wood dust. But if the dust is sticky and the process generates static like sugar, I would recommend an anti-static oleophobic media, or the customer is going to have, again, issues. And the same thing goes for one-piece pleated bags. Lots of options to choose from, depending on the application. For example, if it's a high heat application over 250 degrees Fahrenheit, there are only certain medias that can work effectively at that high temperature. If you know that a baghouse collector is the best solution for your customer's needs, then it's a matter of determining which to specify and sizing it properly. We'll go more in depth on dust collectors and filters during our webinar in November. When I'm designing a system, the next thing that I do after completing all the airflow calculations is selecting and sizing the right fan. The fan has two responsibilities. First, it must deliver the necessary volumetric flow at a required static pressure to drive the operation of the system. Since collectors can operate with clean or dirty filters, the required airflow often has to be maintained over a wide range of static pressure. Secondly, the fan you selected should be able to deliver the desired static and airflow with appropriate energy efficiency at an acceptable sound level. Fan challenges generally fall into two categories: poor selection or poor installation. You may recall that static pressure is a resistance of airflow must be overcome due to system components. It's expressed in inches of column of water, or water gauge. When we design a system, we calculate the total static pressure so that we can size the fan properly. For example, the hoods are calculated at 1.5 inches of water gauge. The ductwork, including straight runs of duct, elbows, and branch entries, total 3.5 inches of water column. The filters in the collector at the filter changeout total 6 inches of water gauge. The filter to the fan ducting is about 1 inch water gauge. So the total system static pressure for this particular project is 12 inches water column. Fans are sized based on system's total static pressure and required airflow. Let's say that I need a fan, for example, and I gave you 12 inches water gauge, and the airflow is at 9,000 CFM. We use the system static pressure of 12 inches and line it up with the airflow at 9,000 CFM. And when we line up those two factors, we land in between a toric backward incline, or TBI, 25 horse and a TBI 30 horsepower fan. So we go to the curve on the right, or where we land, since it's rare to land actually on the curve. And in this case, I would select a TBI 30 to be conservative. See how the static pressure is so important? The required airflow of 9,000 CFM can be delivered really through 3 different fan sizes: a TBI 20 horsepower, 25 horsepower, or 30, depending on the static pressure. Our more in-depth webinar on fan design is scheduled for December. I know it's a long way off from now, but we just wanted to give you a heads up. Next, we have electrical controls. As the name implies, they monitor and regulate the entire dust collection process to ensure efficient and safe operation, maximizing performance and minimizing downtime. They can range from very simple to incredibly complex, like the controls you see here from a system we recently installed. Electrical controls are capable of turning the system on and off, monitoring and controlling airflow, running the cleaning system, displaying differential pressure, which is important to help understand the condition of the filters, alerting the end user when there's an issue, such as when it's time to change out the filters or empty a dustbin, controlling ancillary equipment, such as explosion mitigation devices, and remote monitoring of the system. Because they can be quite complex, specifying the best electrical control panel for your customer can be complicated. The most basic type of control is a motor start. It turns the fan motor on and off with manual buttons, and it protects the motor from short circuits and overloads. A motor starter is often paired with a gauge to monitor differential pressure during the service life of the filters. A basic custom control panel combines motor starter's capability with digital differential pressure reading. It allows the operator to determine set points for cleaning, both high and low. High is when cleaning is initiated for the filters, and low is when it stops cleaning. It's a more integrated solution than a motor starter and gauge. Getting into a more advanced custom control panel, in addition to everything we just discussed, this panel allows for remote interlocks and integration of ancillary equipment like fire suppression systems, isolation valves, explosion vents, rotary airlocks, as well as it typically utilizes a VFD airflow control to regulate the airflow speed coming into the collector. Our control webinar is scheduled for January. To finish things up, and then we'll open up for discussion, there are a few other design considerations to think about. Many dust collector manufacturers are now offering the ability for operators to monitor their systems remotely. At Donaldson, we call our system IQ, which essentially makes a dust collector smart. This allows customers to be able to monitor their collectors remotely. It provides customers with real-time data, alerts them when there's an issue, and provides historical reports. As you can imagine, customers find this incredibly beneficial. Again, most manufacturers are heading this direction, and customers love it. It's definitely something to consider when specifying a system. The total cost of ownership for a dust collection system is another design consideration. How much energy is required to operate it? Where is the unit coming from? How easy is it to get parts? How long do the filters last? How easy is it to change filters out or maintain the system? What is the life expectancy of the system? And lastly, regulatory considerations, everyone's favorite. Each of these agencies may have design expectations to reduce process-related hazards. And as we all know, they're not always consistent with each other. Knowing the hazards will enable you and the customer to make some critical design decisions up front in the process. It can be very expensive and time-consuming to change the device once the equipment is installed and in operation. For those of you who want to learn more about combustible dust, our next webinar on that topic is in February.
All right. Hey, thank you, Jack. As everyone can see, designing dust collection systems is a very complicated endeavor. And that's what we're here for, to help. You can see here, we do have webinars that go deeper into each one of the areas that we talked about today, because it can be very complex. And there's a lot of different ways you can leverage us or leverage other resources to reduce the risk associated with system design or upgrading somebody's existing system. So we're here to help. And as we move into the next area of Q&A, Jack and Amy, I see you turned your cameras back on already. I'll do the same here in a second. And just a heads up, everybody that attended will receive an email with your professional development hour credit. Please note that sometimes it doesn't go through and winds up in your spam folder. If you have any issues with it, please just shoot me an email. My email is on the screen if you don't receive something within a week. Here's a few other QR codes identified on here for upcoming webinars that we have. Also, a lot of our previously recorded webinars, so you can see previously recorded webinars on combustible dust. We also have one that goes a little bit deeper into controls, so you can watch some of those as well. If you have follow-up questions, again, and if you don't get your PDH credit, you can send me an email. And with that, I will turn it over to Amy to go through our series of questions. So thank you, everybody.
Absolutely. Great job, guys. Thank you. So I've had several questions that they just sent to me. First one was, how do I know what air to media ratio or air to cloth ratio to use when designing a system? Any help with that, Jack?
Sure. Well, because this is a basic webinar, there are there are many factors that we kind of touched on, and it would probably be best, because I could spend a long time on that. Quite frankly, more than anyone probably cares to. But yeah, there's quite a few other factors to consider that we didn't go over. And with that also comes into play, besides the particulate and or the process that's being involved in this, the solution that's put forth, air to media ratios, I assume that's what they're referring to.
Yep.
Can vary depending on your selection of equipment. For instance, bag houses can have typically have a higher air to media ratio, but they also have less filter area. So you have to take that in consideration. Cartridges, as we mentioned, if you can use those, is always a better way to go. They tend to have more filter area, but they also have less release properties. They don't have as much energy to release the particulate off of the surface of the filter. So they're coming into situations like that. There are other parameters that we can go over. And if you want someday to talk to me or anyone, we can help you on that if you have a specific application. But to do my 30 years in this short period of time, it would take a long time to do.
Fair enough, Jack.
I'm not trying to be rude about that. It's just the reality.
No, that's okay. I mean, it's one of those things that, people don't know, and they, probably need some help. Very application and dust, dependent. All right. So our next question, do you have any recommendations? Now, this is a little more specific one, Jack, for dust collectors and filters for carbon black in a tire facility.
Okay. With tire facilities, it depends on the process. Is this after the vulcanization process, or is this before the mixture of the material going into it? If it's on the front end before the vulcanization, then you're not going to have as much hydrocarbon issues, and therefore you can potentially look at cartridge collection. depending on the material involved. If it's afterwards in the vulcanization, you're going to have hydrocarbons that come into play. You have to worry about the temperature of the airstream and how that's going to affect the filters downstream. In a situation like that, I would go with a fabric style because, again, great release properties off of it. Typically, if the hydrocarbons are severe, you may have to introduce a pre-coating on the initially of the filters or a continuing process of pre-coating in it to handle the attack of the material, because that hydrocarbons will cool down and cause a tackiness on the filters, and then it kind of gums up the filters, for lack of a better term. So it becomes an issue. So
Okay, so that's why the pre-coating part of it is critical, right?
it can be, yes, and it might
Okay.
be having continuous pre-coating in that if that's required on your hydrocarbons. Again, depending on the temperature when it gets to the filters and the properties involved in that vulcanization process, because it does thermally change the chemical composition of the materials through that process.
So Jack, on that second process, maybe I missed it, were you recommending a bag house then on the?
On the vulcanization, that's typically what I would look at because, again, you're going to have a lot of hydrocarbons on that,
Okay,
John, and that becomes a sticky proposition, so to speak.
all right.
What words there?
Gotcha. All right, so here's another specific one for you, Jack. What filtration media do you recommend for gold smelting fumes, lead emissions, and borax?
Okay, when you get involved in any kind of smelting process, a lot of times you have to they use a dross process, which is adding organic material to take out impurities, and you have to be very careful on that too, because that will create sparks and embers into the system. I've used cartridge collection downstream of those processes in the past, along with a fire suppression system because of the sparks and embers and such. They've been successful. Be very conservative on your air to me ratio, especially with lead.
All right, thank you. Do you typically recommend, or is there any, pros and cons of putting a collector inside versus putting a collector outside?
If you can put it inside and there's no issues, regulatory or concerns, that would be the way to go. The advantages of that is that your temperature doesn't change, which is helpful. And if you take it outside, depending on where you're located, you're going to go through some dew points possibly if you're not running 24/7. So that is a concern. But in many cases, you have no choice but to put it outside, because if the dust is combustible, you have sometimes no choice. But there are concerns about dew points and such, depending where you're located. If you can't return the air back in the building, where you're going to have to make it up with conditioned air, as you know, and that becomes a costly solution.
And
Gotcha.
if you're inside, Jack, obviously you might want to consider sound mitigation and silencers, right, to reduce sound if you're a bigger collector.
Yes, if you return the air back in the building, you got to watch that inrush of clean air coming back in, and that can be regulated through a silencer or through further mitigation of a secondary source filter, like a DOP or a HEPA filter, to expand that return air plenum coming back in the building, which will lower the velocity down. Or you could put in with socks, perforated socks that are used quite often in HVAC applications.
All right, thank you. Next question, also about collectors. You'd mentioned that you tend to start with a cartridge collector and you don't move on to, think about other types unless it won't work. What are some examples of where a cartridge collector would not be the best choice or won't
Um,
work?
is that is that your question, or is that actually a person's question?
Yeah, that's it. Sorry, I'm trying to summarize. It's kind of
Oh,
a little
gotcha.
longer question, but yeah.
No worries. So where a cartridge collector would not work really well, is that what they're asking?
Yeah. Where would
Okay.
examples where, because you it said, I start with the cartridge, but where would it not work?
Sure. Um, it could be like we talked about, hydrocarbons would be a concern. Moisture, dew points, depending on the dust that's being captured. If it's hydroscopic, as we talked about, um, potentially abrasive. Those are things that I would be concerned about going with a cartridge. Sometimes also fibrous dust. If there's long fibers involved in that, that might not be a way to go with cartridge. So you might want to look at a bag style. Now, When you get into some of those, you can change also the shape of the bag, or look at units that have an envelope style bag with a downflow design like we have, or you can go with a traditional bag house, which is an upflow design. Be careful on those, depending on the particles, because you and what's in the airstream, because you're going to deal with can velocity as it goes up to the filters. I'm not a big fan of typically of going up towards the filters. We've learned that in Donaldson that you have, you're feeding an airstream when you clean the filters, so it's constantly keeping that dust suspended towards the filters with the lower style ductwork going upward.
Thank you, Jack. John, this one's probably for you. Are there any plans to have additional sizing or selection, maybe software, or a little bit more assistance on Donaldson's website in the future? Any idea?
Ooh, that's a good one. I mean, it's always tricky because of the unknown elements, right? We have one of our common phrases, well, it depends on this scenario and how far you're. So factoring airflow is very, very tricky. Probably the one thing that we are looking at and we can consider is our trusted the ductilator, right? Which helps you with some sizing. It gives you some guidance on the different velocities that are needed per the different contaminants that are out there. And if there's a way for us to digitize and make that more readily available, I know that there's online ductilators. We have our own ductilators. Those help with airflow calculations. Um, that's a good point, and I think I could probably take that to marketing to say, okay, is that something we can incorporate into our new website? But if anybody is interested, again, ductilators are great. We do have a ductilator. You can shoot me an email, and I can ship one off to you too. They're pretty slick little units. I'm not sure. Yeah, kind of like this with little flow diagrams. I'm not sure if you can see it very well, but so a little grid that works. But it is tricky because everything's to allow people to calculate it themselves, and we'll work on that for sure.
Gotcha.
Yeah,
And in
there's
the
a
meantime, of course, they can always reach out. We have local representatives all over the place. We can certainly help you out for specific applications with that part of it because it is a little complicated.
Yeah,
Um,
I see some people are putting some things in the chat right now about that. So there's different resources, but
yeah.
Yeah, I agree with John. I want to add on to that it's the old adage is too little information can be dangerous. There's
Hmm.
a lot of variables that come into a solution process that we didn't address in this basic webinar. And yeah, it takes a lot more than just simple things put onto a graph, in my opinion, or into a chart.
Thank you, guys. All right, so our next question is about cartridge filters. Can you talk, Jack, about what's the benefits or difference on the different shapes of filters?
Well, that is a good question. It depends on what selection you choose. Just like bag houses, cartridge collectors can have a downflow design where the air comes down towards the filters, or it can have an upflow design. We tend to go with a downflow design, so we have different types of shapes of filters for that. You said this is for cartridge, right? You said?
Yes. Just
Okay,
wondering what's with the different shapes?
yeah, so the different shapes can aid in the airflow patterns inside the dust collector to aid on the removal of the dust once it's pulse cleaned. So that's the reason for it. We happen to have on ours, we have a more of a horizontal design. We actually came out with vertical hung cartridges when they initially started, and we found limitations to that, especially with very fine dust. And so we went with a downflow design, and we've changed the shape of the filters to aid in the airflow pattern and the removal of the dust once it pulse cleans. So the latest designs that we have is a DFE design, which is more of a pyramidal or moidal, a triangular design, which aids in having the surface area on top of the filters be less, and the bottom of the filters, which is not exposed to the airstream typically, have more surface area. So there's no chances of that dust clinging up or staying on the surface. So it helps in aiding the performance. Again, depends on the process and the particulate being used and what your solution is, but that's the reason we've gone to that typically. On mist collection, we've gone to more of a rectangular style shape filters because it gives us more surface area than a round filter in that collector.
Gotcha. So it's really about the optimizing the collector in terms of and the media in terms of surface area per filter, right?
Correct. Well, and performance, yeah. With
And
the
right.
performance, yeah. It just aids in performance of the filter performance either during it or on pulse cleaning too.
Okay, thank you. All right, so next question. Does Donaldson offer a type of dust collector that can be used as a fresh air intake ventilation unit in a mining plant? So it's very specific.
Actually, I'm working on a project very similar to that.
Really?
Yes, with an OEM. So the answer is yes. We take in consideration the dust loading that's going to be probably less than a typical dust collection system. So you can go normally a little bit higher on AMR to handle that process. But yes, it can be done.
Okay, thank you. And the person that's asking that question will reach out to you as well to give you a little bit more information about that.
Yeah, and if I'm not the
S-
person that's in the area, I can defer them to another qualified person.
exactly. Thank you. Appreciate that. Okay, let's see. Someone's asking about, I'm not quite sure I'm understanding the question. Do we have dust size-wise velocity? John, do you understand what they're,
Yeah, I'm looking at the, that ductilator that I shared with you. There's, on our ductilator, we have grids for velocity, whether it's a vapor or whether it's a average industrial dust, it's a heavy dust. And these, I think, are coming off of, recommendations from the ACGIH. So there are velocity recommendations per size or type of contaminant that, again, if that person just wants to shoot me an email, I could send them one of our ductilators that has that spelled out. I'm sure it's available in other resources as well.
thank you. Yeah, or we can get you just some general information. We can email that to you as well.
Yeah,
So
it's pretty
thank you.
standard industry,
Yeah.
guidance on these velocities.
Yeah, be careful on that too, as John and Amy know. The particles are one consideration, but you have to look at the whole process. So let's say there's
Right.
embers involved in it, as we talked about earlier, as you guys know. You don't want to collect those in high velocity, even though the particles might be, well, it's conveyed at a higher velocity because there's no issues on abrasion. Well, that's true, but you might have embers or it's abrasive dust. So there's things that come into play besides the particle size.
Yeah,
That's a good point. So there's a general chart, but it still could depend, right?
if
On
it's
other factors.
combustible, you go to 4,000, right?
Right,
You have to go straight up. Yeah.
right. All right, thank you. So our next question is about wood shop applications. What are your thoughts on PVC piping for ducting? So a wood shop, that must be dry dust, so I'm pretty sure you're going to say wouldn't recommend that, but and then can you also expand on grounding requirements for wood dust? So let's start with types of ducting for wood shop applications. What would you recommend?
Well, PVC would never be suggested, and when it comes to wood dust, we would definitely stay away from that, as we all know, because it creates potential static, and static can create sparks. Another reason you want to use PVC is it's really for fluid, and air is not. Sometimes it acts as a fluid, but in this case, you have to be concerned because they have tight elbows in PVC ducting, and that is a concern because you're going to create a lot of static. So when it comes to grounding, there, and I'm going to defer because I'm not as good on the grounding experts, but you have to be able to be grounded. Typically, it's every 10 feet or so, sometimes 15 feet. You want to be able to ground that ductwork to an existing building frame or structure that you can dent it to ground and be able to handle that. That would be a process to do it. And sometimes the collector needs to be grounded too. But those are the things you look at if that becomes a concern.
Okay, so we'll get you, so the person that's asking questions about wood shop applications, we can also reach out and get more information to you as well. So when you said, so PVC piping, would you really just recommend it for mist, if anything, Jack?
I wouldn't recommend it at all.
Okay, all right.
Just
So
because again,
definitely
you have tight
wet only.
yeah, you
Right.
have tight elbows. Again, it's
Yeah.
designed for fluid, not really air.
And we do get that question a lot, so I'm glad that someone asked that. Next question, do you recommend a dust collector for a solvent-based ink plant? What would you recommend? All right, so solvent-based ink plant. Any collector recommendations that you can think of, Jack?
Well, you have to be careful because is it just solvent, which is then off gassing? It really is not going to be a filter concern because you can't filter gas.
Right.
If there's other things in that process, such as droplets that you're trying to take care of, well, that can be addressed, but you cannot take care of gas. The other thing is with solvents is going to be highly combustible and potentially flammable. So you have to address that also. So those are concerns that you have to deal with in your thinking process on a solution.
Okay, so again, another person that we'll reach out to get you some more specific information, because that sounds like a bit of a complicated situation.
It is. It is. I'm starting to sound like a lawyer here. I apologize, but there's a lot of complex.
Well, a lot of times the answer is, well, it kind of depends, right?
Yeah, right.
All right. So here's our next question. Let's see. If the site has a large collector system, considering future loading, so 70% bigger fan than the current load, what would be the options to keep the velocities appropriate in the headers? So they're looking at
So,
expansion.
right. So they're going to address future expansion, but the
Yep.
current system is going to be smaller, basically.
Yep. Yeah.
So how do you address that? Well, you can do it a couple ways. You can put the existing system in and have a barometric damper on the main header going to the collector. That would be one way to do it. So you're bleeding in air all the time. Or you go with a VFD solution. We're not saying you can't go with both, but you go with a VFD solution on the front end, drive your fan down and operate at that lower CFM, but have the diameter, have two runs. You could have two runs in it. So you have the existing run running in a lower one. And if you have the further expansion, you can have a separate run and tie it all in when it gets to the dust collector. If it's combustible dust, then you have to take that in consideration and you'll have to branch in with a header and then go with isolation devices when that goes in and change that out or put it in now and bleed in there. So there's different things that can be done. It's not as easy as talking on here, I guess.
I don't think anything is on this topic, right? All right, so here's your next question. What type of collector would be recommended for a cotton gin application?
Cotton gin. So we're looking at that. I'm up north, so I don't get into that as often as maybe people down south, but I will try to address it from my experiences. Um, you're going to have potentially longer fibers in that, so you have to be very careful on that. So with longer fibers, you're going to have bridging concerns. So I would go with a downward, if it was our equipment, I would look at our Dalmatic that we have, which is an envelope style bag and has airflow coming downward towards the filters with quite a bit of pleat spacing between the filters. So you can take filters out of that existing collector and increase the spacing between them, making the space wider. Obviously, that reduces the amount of filter media, so you have to calculate that in, but that's what I would go with typically.
All right, thank you. Sorry, I'm just kind of filtering through some of these other questions. I think I pretty much got most of them. John, do you see any that I missed?
No, I think you got most of them. There was a question about the NFPA standard. And I think for every application we make sure we understand and work with again the local project owner to understand the DHA. Are they meeting what regulations are required to be met in every scenario? So yeah, I think we could work on that one off on a project basis.
Okay. Sounds good. Well, thanks to everyone for joining us today. We appreciate it. Thanks for all the great questions.
Thank you.
And we will reach out to people who had individual questions as well and make sure that all of your questions are answered.
Thank you all.
Thank you.
Thanks. Have a great rest of your day.